Start recording since it didn't ring that one time, and I'll start the screen share so I don't forget to do that. So welcome back, folks. Hooray! Yeah, hi Zoomers. How we doing? So. We're like halfway through the semester already. Can you believe that?
Believe it or not.
Believe it or not, yeah. It's stuff's getting real, isn't it? I think we're all kind of in a similar situation here. I wanted to make a couple of announcements. So homework is not due Monday, it is due Wednesday of next week. I'm going to ask in just a second if anyone has questions, so I'm happy to go over things as a group if that would be helpful. And next Thursday, we are getting kicked out of our classroom for comprehensive exams again. So we're going to be meeting on Zoom that day instead. And I believe that should be the last time this semester, but we'll find out. Otherwise, so yes, homework questions. How is that going? You're done. Okay. I peeked at the database, and there are many folks who are not done. So if you are one of those folks and you would like to get some assistance with anything, I'm happy to help. Yes.
Do you have the quadratic formula? Explain again what is the difference between the intercept and the first slope?
Okay. So are you thinking of it in physics terms, or are you thinking of it in like stats terms?
More in stats terms.
Okay.
Like when we centered, so for example, when we had in our notes, like slide 29.
Slide 29. Okay, let me pull that up here. This one.
Yeah.
Okay.
Okay, so I get that the intercept is our expected increment at age 18.
Yes.
But what is the linear age slope then looking at?
So it is still the change in y for a 1 unit change in x. That part hasn't changed. But because of the quadratic term, this linear slope is conditional on when time is 0, or excuse me, age is 0, wrong class.
Okay.
We're talking about the same thing in both classes right now. So this is the rate of change at 18 specifically, or this way for you. And then as age goes up, the slope starts to slow down, and it eventually flips over because there's a negative quadratic in this example. That's making the slope less positive as age increases.
So, but that's just for age 18.
Yes, every unique value of age has a potential different slope, but there's a function that dictates how it will change. It changes by twice the quadratic per unit of the predictor.
Okay.
Does that help at all?
Yes.
Okay.
Thank you.
Yes. So we refer to beta 1 in this example as the linear slope because that's what it would be, right? Like previously it was just, well, this is the slope for age, and we didn't have extra words on it, but because there's two different kinds of age slopes at work, we need more specific labeling. So the linear slope is that one, and the quadratic slope is this one. And this is, if you're thinking of it in physics terms, the intercept is like position, beta 1 is velocity, and beta 2 is acceleration, if that helps at all. I hated physics. That's not going to help me. But in case, someone else is better at physics than me, which odds are very good. Okay, other questions on homework right at the moment, but then more generally? No? Zoomers, we're good? Okay, well, yeah, it's not till next Wednesday, but I just, thought I'd ask. We have 2 examples to finish up today, piecewise models, and also a piecewise model, but from a slightly different perspective. Should we look at that stuff? Yeah? Let's go back to the piecewise model for education. So this picture and this coding scheme. So there's some vocabulary that I realized I don't think I defined. The term knot point or break point is where the slopes break apart. So in this instance, we have a knot point at 11 and another one at 12. The intercept is also at 11. So in coding these things, it can be convenient if your intercept is the knot point, but it doesn't have to be. So I actually thought, before we do this, I'm gonna do something else. I had an idea. I think I like this idea better. We're gonna play along and look at a couple example coding schemes. So let's say that I have a variable that's x ranges from 1 to 7, and I want to create one slope that goes from 1 to 4, and a second slope that goes from 4 to 7. Okay? So I would say then that the not point is at 4. What if we wanted to have our intercept at 4 as well? Could we do that? I think that's the easiest one. Intercept equals 4. So what do I need to do first? Besides make that bigger. There we go. If this is what I want, help me fill in the boxes here. So first thing, define my intercept. If I want it at 4, what should these two new predictor variables be coded as? Zoomers are typing? Zeros, yeah, because the intercept is the predicted outcome when all your predictors are 0. So there has to be one point that's zeroed out like that as the reference. So if I want the first slope to track 1 to 4 only, what needs to go after 4 to make it shut off?
0.
Another vote for 0? Nodding Zoomers, yep. Likewise, if this other slope is only supposed to track 4 to 7, what needs to go here to ensure that it hasn't turned on yet? 0. Okay. Good so far? All right. So now what goes here? If 4 is 0, then what is 3? -1. What is here? -2. -3. So a more efficient way to write this would be something, and this is like pseudocode here. If x is, we'll say, less than 5, then x1 to 4 equals x minus 4. So that would be a faster way to write this. And then the other half of it would be if x is greater than 3, x1 to x4 equals 0. Yeah. So this is what it will be in practice, is figuring out statements like this that makes this process a little bit more generalizable, rather than so you don't have to come up with every single unique value and what it would be. Now, what are we missing? What goes here? What? Yeah, 5 is one more than 4. What goes here? 2, 3. So now we can finish the story. Like, I'll add to this one. If x is less than 5, then the second variable, x4 to 7, equals what? 0. And then this one would be x4 to 7. If it's greater than 3, x minus 4. I'll fill that out. So your next homework after this one is going to look like this. Two-slope model. And along these lines. Now, what if we want to make it a little more complicated? And I'll put this up after class, by the way. I always do that if I draw things. What if I want to change my intercept to be the first value instead, but I still want my not at 4? Can I do that? I can do anything I want. All right, take that out. Okay, so if the not is at 4 and the intercept is at 1, what goes here? 0's for both, because that's my intercept. Zero that out. So the first variable is supposed to track the change from 1 to 4. What goes here? If 1 is my new 0 point, how much further? 1, exactly. What goes here? What goes here? Okay, now what goes here?
0.
Oh, that's a guess. I mean, I'm going to put a question mark behind it. If I have a 0 here, it's going to put me all the way back down to where I started. But I want to do is shut it off where I left off. 3 instead. Yep, it stays at 3. So that would then create like a slope that's going up, for instance, and then levels off. It would look like this.
It would not contribute more.
Otherwise, it's the predicted value would go all the way back down, and we don't want that. So over here, if the knot point is at 4, what goes here? Well, it hasn't, this one is still active on the other one, so this one would be 0, and then this picks up where it left off, like that. So it's up to you where you put your intercept. The question would be, like, what do you want as your reference point? What are your baseline for what these variables mean? And the knot would be dictated by, you know, what range, like clinical versus subclinical was an example we had, whether you're in, you know, a before versus after for some kind of intervention or something like that. The one that we're doing in education is a little bit more complex because it has 3 pieces to it. So I put the intercept at the first knot point here at 11. So that's why it's all yellowed out here. So this follows that pattern. The first slope is trying to keep track of x less than 12. So it goes 11 is 0, that means 10 is minus 1, 9 is minus 2. And then it shuts off at 0. Then the second one kicks in. And it says, hey, did you graduate high school? Yay for you. You get a 1 here. But then it shuts off because it's only tracking just this much. And then the third one's like, oh, wake up, it's your turn. It's like a relay, like they're passing the baton to each other. And so this one then is 1 at 13 because this one left off at 12. So the idea is that income has one relationship to education in people who did not graduate high school. There is a potentially different relationship. The effect of graduation, essentially, is what this middle piece is. And then what is the continuing effect of additional education if you're already a high school graduate? So 3 different kinds of research questions that would be going with this type of specification. Okay, how are we doing so far? Zoomers, we're okay? Ish? Thumb check?
So I have one question. I'm just,
Question.
I don't know, confused by the third slope.
Mhm.
Why is it not shutting off at 2? Because the way I see the graph going up, the third graph.
Yes, this over here?
Because the first one is going to be the 0 and then it shuts off. The 1 that goes up and then it's stable.
Mm-hmm.
So the second one should go further up and it should be stable there. Rather than being stable, it's going all the way to 6. Up.
Are you saying that the 3 slopes don't look like they fit the picture? Is that what you're saying? Or are you questioning why the third
Yeah, I'm
slope
questioning
is
the numbers.
the numbers?
Yeah.
Okay, so the general idea is that the values should leave off at the highest point.
Okay.
So like this one ended at 0, so that's where it stays. This one switched from 0 to 1 here, and to shut it off, it stays at 1.
That's fine, yes.
Okay, and then this one continues because it's indexing everything past 12.
Okay, so it's going to go all the way till 12. But
All the
here-
way to the maximum level of education,
Okay,
a linear
okay.
slope.
All right.
And I would agree with you that does not look like it matches the picture. But for your first piecewise model, I didn't think 3 slopes with the quadratic would be, you know, fair, right?
All right. Right, thank you.
Okay, other questions? So then to accomplish this in the code, I figured out what functions would have to look like based to fill in these values, rather than making them fill in directly. So I initialized to missing in both programs, and then systematically filled in based on conditional logic. So if education is less than 12, then the function should be education minus 11. That would create these values right here. If education is less than 12, the second one should be 0, and the third one should be 0. So we're filling in the first, 3 rows of the table. Then if education is greater than or equal to 12, the first one is shut off at 0, the second one is shut off at 1, and the third one is education minus 12 instead. So 12 is the new reference point for the third slope. That's where it starts. Question?
No.
No, okay. Just hand gestures.
Yeah.
Same thing in R, just with additional language required. So the which function in here is isolating which rows are relevant, and it goes in both spots here. So if the original column of education is less than 12, then do these things. Otherwise, if the original column of education is greater than or equal to 12, then do these things. And we end up with education minus 11 as how the first slope is created, and then minus 12, and that should still be blue. Here, I'm going to borrow it. There. I think it's helpful to say things in the right color. And yes, I end up having to manually color quite a bit of these things. Anywho. Do you remember what happened? I left you with a cliffhanger. They're like, what? I did. I did. It was reviewer 3. It's always reviewer 3. So here's what happened. We are going to look at, this is data output, it looks like. Do I have this in R2? Some of it. Okay. All right. So we have how many fixed effects in this model?
This model.
In this model?
4.
4. How many slopes? 3. How many intercepts? 1. Excellent. And this part would be what builds y hat, the predicted y. So if you have a 10th grade education and someone else has a 10th grade education, you have the same predicted y hat. So there's a lot of room for variability still, because everybody who has the same value for education has the same prediction according to this model. So does this model significantly predict income? Where do I look? What am I looking for? Oh, there's lots of p-values. Which one?
There's lots of them.
There's lots.
We'll just choose one randomly. Good idea.
I can count like 5 p-values in front of me. Which one answers the question about the model as a whole?
That one on the top.
The top one. Yeah, this one right here. So this is the p-value that goes with the f. F is always going to be positive. F is in squared. It's essentially how much information has been captured by the model relative to how much is left over. And each is weighted by the number of slopes. So how much per slope spent, how much per slope left over. So ideally, then this would be greater than 1. It's 47, so that's good. What would be the corresponding effect size for this test statistic? I heard it. Say it louder. I heard it, I swear. Am I hallucinating? I could be. This is water in here, I swear. R square? Yeah, that thing. 2 different definitions? Give me the easy one. Easier one, I should say. It's a proportion.
How much is explained?
Yes, how much of the total variability in our outcome has been explained by the model as a whole. 16.43% R square is given as a proportion. What's the highest R square can be? 1. Yeah, what's the lowest it can be? 0. When would it be 0?
No coordination?
No correlation or empty model, right? Like no variance has been predicted. If you have no predictors, you can't do any predicting. And if an R square were 1, what does that mean?
Perfect.
Perfect. Yep, that means E is gone. E is 0 for everybody if R square is 1. You know how you could do that? There are 734 people in this data set. If I took person ID number and I treated it as a categorical grouping variable, I could explain all of the variability. Now, would that be a useful endeavor? It would not. But that is a strategy by which sometimes folks address multi-level sampling designs. So for instance, if you're interested in children, but to get enough children for your sample, you have to borrow them from 5 different classrooms. Well, technically, that's a multi-level design where you have classroom differences and child differences. So it's kind of like you would end up with 2 different kinds of E's in that type of model. Well, if you only have 5 classrooms and you don't really care about them, you could treat classroom as a categorical variable, essentially put in a dummy code for each classroom, and then there would be no more classroom differences to worry about. So that does make sense if you're thinking of the units as nuisances that you want to get rid of their differences. But if you're interested in why people differ from each other, putting in person ID as an explanatory variable is not the best strategy. So just as an aside. So this is a decent model, so 16% of the variance. We can also think about it as a correlation. Yes, if I unsquare this by square rooting it, that gives me down to R. It's the R between what and what?
4 and 4.1.
I'll give you a hint. One of them is Y. The other one has an accessory.
Y hat.
Y hat, yep. I'll have to show it to you later point. Up in my office, there is a hat that my husband got at a conference, and it is a theta with a hat over it, so it's a theta hat, because psychometricians have a great sense of humor. So theta hat. So yes, this is the square of the correlation between actual Y and Y hat that's built from this part. So to say that more directly, it's the correlation between education and income, but it's education as put together this way, with 3 slopes instead of 1. So education as an overarching concept is responsible for predicting 16% of the variability in income in this data set. Okay. What's this number? 159. It is mean square residual, and what do I call it? Residual variance. It's the variance of the E's. So if I take E, square it, sum it up over all the people, and divide by n minus 4, because I have 4 fixed effects that it took to get to those E's, that's where that number came from. The 190 below it here under total is what the variance of the E's would be in an empty model. That is the sample variance of this outcome variable. Yep, good job, Zoomers, too. All right, then in terms of the individual slopes themselves, the constant, let's do first, that's the fixed intercept. 8.5 is the expected amount of income for what kind of person is my reference. Where's the intercept? Not quite.
Oh no, junior.
We'll go back up to my table here.
11.
11, yeah, high school junior, we would call it, 11th grade. Yes, 17 or 18, depending on how you roll. I was young, my birthday is in September, so I actually graduated high school at 17.
Me too.
Every year they'd be like, really, you just turned 15? Really, you just turned 16? Like, yes, I'm sorry. But they weren't as strict about that back in my day. So an 11th grader is predicted to, or someone, excuse me, who has 11th grade education, let's put it that way. This is a data set of working adults. Is expected to make $8,530 some dollars a year. What happens if you have less than 11th grade education? Negative. So as education goes up, income goes down a little bit. Yeah, by like $200 or so, not significantly. So do we retain or reject the null hypothesis? We'll go back to that language. Or do not reject is the other way people say that, but that's a double negative. Retain. Yeah. So we're not accepting the null, but we're saying there's not enough evidence to say that this is different than 0. If the true slope in reality in the population were 0, we would see one that is this big in absolute value or bigger 65% of the time. It's well within expected territory within the goalposts. What about if you graduate high school? If you move from 11th grade to 12th grade in terms of your education, what happens? It goes up by $4,680. Is that significant?
Depends on your goalpost.
It depends on the goalposts. So alpha, your type 1 error rate, your chance of making a false positive should have been decided ahead of peeking at your results. If we went with the traditional alpha of 0.05, then yes, I would call this significant. If you were being more stringent because you were worried about making too many false positives, then maybe this wouldn't be by that standard. How about if you keep going in school like you all are currently doing? What happens? Up by 2.12 for every additional year past 12. And the standard error for how inconsistent that slope would be, the average discrepancy of this sample slope from the population slope is only 0.2, so that translates into a t of about 10. So estimate divided by standard error is where this column comes from, and that's 0 to several decimal places for the p-value. So this is like 10 standard errors away from expected. Very, very into unexpected territory. All right. Now, where I had left off with then, what if reviewer 3 comes back and says, hey, I think this model is over-parameterized. That's a fancy term that means too much stuff in it. I think you should just have one slope. How do I respond? Which one do I want to keep? Okay, so the question is, how can we think of this as an empirical way to defend our choice? Is there a way we can test whether we just need one slope, or whether 3 is better, or 2 is better? What would the 3 slopes look like if the true relationship were just straight linear the whole way through?
Equal or relatively equal?
Yeah, they would all, they would be broken still, but they'd all follow one line. So another way of saying the same thing is we can test the differences between these slopes. Because if the slopes are different, then we can't just use one. Now, do you know how to do this? Do you think you know how to do this? Don't ask the Google. Ask me. They pay me to teach you. You actually already know how to do this. The exact same technology that allowed us to test differences among the non-reference groups, or to make linear combinations of parameters to create expected values and things like that, we're going to use to do that. So I'll show you in both packages, first starting with Stata, LinCom. I take first less than high school slope, and I multiply it by -1, and I add it to the graduated high school slope of 1. So that's a fancy way of saying I'd like this slope minus that slope. That's what the negative does, is it creates a subtraction instead. And I'm writing it this way because it matches the way that the other programs specify it. Obviously, like the ×1 here doesn't do anything, but the numbers will match the other packages. So this slope then, the less than high school slope was this number, minus 0.26. The graduating high school slope was 4.68. The difference between them is a positive 4.95. So the grad slope is more positive than this one by 4.95. And is that significant? We follow standard error, T, P. Yeah, depending on the alpha, but if we go with the traditional one, sure. So far, reviewer 3 defeated. The first slope and the second slope are statistically different from each other. They should not be forced into being one thing. How about the second versus the third? Well, now we have 4 versus 2. So the difference is negative 2.5. So 4.7 versus 2.1. How would I talk about this one?
There's justification to combine them.
Yeah, reviewer 3 might have a point. These two are not different from each other. However, I would probably not want to report this model anyway because of how bad this part looks like it fits. Like this linear slope through here needs to be some kind of bendy something, I think, to adequately capture that. And then once I do that, then I don't know for sure if this slope and that slope would be different from each other, because it just depends on how things are set up. And I've never actually tried, but if you want, if you need a challenge in your life, if you don't have enough to do, go for it. Fit an extreme piecewise model and tell me what happens. I've never played with these data for that before.
So then, for this part, if we're going to see if the slopes are different, then you're gonna have to have an idea of what your graph looks like
Mhm.
for your slopes. Because you could end up choosing two slopes that aren't different, but it's still not a good idea to combine them because of what's going on in between.
Yes, so the comment was you have to sort of pay attention to the context of your data and the patterns, right? To decide how many slopes you need and where the knots would be. So this is guided by not just this picture, but sort of what I know theoretically about the educational system and where things should shift. Like there's a huge difference practically between 11, 12, and 13. There are models, by the way, that find the knots for you. That's not something we can get into in this class, but they exist. They're called latent. The term latent means the computer's going to find it for you. It's imaginary as a general principle. But yeah, you can you can essentially create a parameter out of where the knot is, and it tries to figure out what the best point would be to break it. But yeah, otherwise, like your choices for how to set this up, the number of slopes and where they break, should be based on the patterns in the data as well as some sort of theoretical expectation of the construct that you're talking about. All right, R folks, I didn't want to leave you out. By the way, for your next example, I have finally learned how to do functions, and I'm very excited to show you much more streamlined code. I'm having a lot of fun playing with it to make it do stuff, but well, that's next week. So this is the usual setup for linear models here in R. Supernova prints the sums of squares table. I am saving the summary to do stuff with it later. The slope comparisons are this part. So let me zoom this in here. So I'm using a function called GLHT to do this for linear combinations of fixed effects. That's general linear hypothesis test is what that stands for. These are the labels that I wrote as breadcrumbs as to what this is for. I would highly recommend that you change these to be whatever yours are so that future you is like, what the hell is this? Like, there's no ed in my data set. These values right here are multipliers. They multiply the fixed effects. So this first one, my goal is to create a difference between the first education slope and the second. So that's why the intercept is zeroed out, because I don't need it. Likewise, the third slope is not relevant to this estimate, so I don't need it. So this creates second slope minus first one. So first is the reference for this. Likewise, contrasting the second slope versus the third follows the same pattern in which the intercept and the first slope are zeroed out because they're not relevant. So then the rest of this saves it and prints it and adds confidence intervals. Okay. Effect sizes then. That's the missing piece that's not provided for you. So right now, all we know in terms of effect size is one number, the R-square for the model. Now that is a general effect size that describes how effectively this outcome is being predicted by everything in the model. Complementary information we would want to give is specific effect sizes for each slope. So I want to show you how to make the programs do that for you because it doesn't spit it out directly. And this is the thing I'm building functions for now to automate. So in Stata, this code you can copy and paste directly and not change any of it, okay? This is accessing saved results. The key is that you have to run it right after the thing that you want to access. So this lincom is what it's going to save, and so it's the estimate divided by the standard error, and then the square root of that plus 2 times degrees of freedom. So that is the formula for partial R. I did the same thing then, so no, this is exactly the same code, just repeated down. But now it's going to refer to this one instead. In R, where these are being pulled from, save model ed, is me saving the summary of the save of the GLHT. So this is very cumbersome, but I had to work with this because of the way things are saved. It takes like multiple layers of it to do math on things sometimes. So this is what I'm trying to make a function for that makes your life easier. But this also is code that you should be able to use directly once you change the name of the object to refer to what you called it in your example. So this is where find and replace would be your friend. So this is the result of the GLHT. This is the result of the model. And then I concatenated the table so that everything was in one. So then this is the fixed effects from R with an extra column that I just built called partial R. So these are correlation metric effect sizes. They describe the unique effect of each of these things. That's a concept that we'll talk more about next week, actually. But these would be specific effect sizes that go with the general one. And then I can also do the same thing with respect to, so this was for the fixed effects, and I can do the same thing for the GLHT results. There's also a package I found that spits out partial correlations in R, P-core test, and so I have an example of that. This one is a little more typing because you have to do it like for every combination of what you want. So less useful for that. And then, as usual, words. Lots of words. Yeah, well, words are important.
They are.
That's where you translate what you found to people. And so you'll note that most of my sentences have the same pattern. It's like, we found something, stat, 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 comma, indicating that or such that. And then that's the part that the people who are reading this would actually like highlight and pay attention to. All right, 2:43. We're going to finish this today. I can feel it. We got one more example. Similar idea, slightly different context. So let's say that someone asked you on a scale of 1 to 5 how happy you are. And 1 means unhappy, 2 means neither happy nor unhappy, 3 is fairly happy, 4 is very happy, and 5 is completely happy. Now you don't need to answer this. I know better than to ask that question legitimately in a stats class. But just in your mind's eye, right? Yeah, of course you're completely happy with this. Duh, this is the best stuff ever, said no one ever. Now, my question that I do want you to answer, are these numbers? No. Well,
They're numbers, but they're ordinal?
They're ordinal, yeah, like, can we think of them as actual numbers that like an integer interval representation? No, I don't think so. Now, these kinds of scales, though, are very commonly used as numbers. There's an empirical way to decide whether you can treat this as a number, because what that essentially translates to is, can you fit one linear slope through it? So if, like, these are the means, yep, this is the plot I have here. So I have the black line here is the means for each of these. The red line is the plus or minus 1 standard error around it. If a linear slope holds, that's like saying the difference between 1 and 2 is the same as the difference between 2 and 3 is the same as the difference between 3 and 4 is the same as the difference between 4 and 5. That sounds like interval to me. So you can treat it as interval if a linear slope is an adequate representation of how it relates to this outcome, is what I would argue. If it's not, though, then you wouldn't want to do that. So I want to show you a coding scheme by which you can test this more directly. It's a different kind of dummy coding scheme than what we did before. So rather than doing indicator dummy coding, as your textbook refers to it, we're going to do sequential dummy coding. And it's based on the same logic as the piecewise slopes. Essentially what we're going to do is create 4 successive differences. So I'm going to set the first level of happiness, the 1 response, as the intercept. And then I'm going to have a predictor called H1, V2, 1 versus 2. That's going to capture the change in income for someone who gave themselves a 2 rating versus people who gave themselves a 1 rating. And then it shuts off where it left off. So note the 1s. The second one picks up here to capture 2 versus 3, and then it shuts off. Next one swings in, next one swings in. So the means look like this, and just from this pattern I can tell you a line is not going to be a very good fit. Like, each of these lines looks a little bit different from each other. Now this is different than the coding scheme we used for group, and the difference is right here in this red box, the 0. So in this lower example here, this is called indicator coding, each of these contrasts is relative to low as a reference point. So this is low versus medium, and this is low versus upper. Over here, only the first one is relative to the reference. Each is relative to the next one instead here, because the slopes don't go back to 0. They stay where they left off. So it's like a stair-step function, essentially. I would argue that if you have an ordinal variable, this kind of sequential coding is probably more useful than comparing each successive category back to the original. If you have nominal data, so like the groups are not ordered, then this would probably make more sense. Okay, does that make sense? So if you think of these as like switches, right? This one turns on right away, shuts off. This one turns on at 2, then shuts off. Turns on at 3, and so forth. Well, here's what we're going to find. There's a lot of information on here. So how many slopes are in this model? How many slopes? 4. How many fixed effects? 5, yeah. So what I have here is beta 0 is the expected income level of people who said they're unhappy. They make $15,000 on average. Then beta 1 captures the change from a rating of 1 to a rating of 2. That change is 1.69, but the standard error is twice as big. So p-value is 0.63. What would we call this? Bleh. I would call this positive, but non-significant. Next one over. The change from 2 to 3 is directly captured by the beta 2 slope. And that one went down a little bit. Also non-significant, though. Beta 3 is capturing 3 to 4. So it's just like a little stair-step function. This one,
Very close.
yeah, very close. This one would be another, what's your alpha? What's the question? And then the last one is negative 2. So we have a positive, then a negative, then a positive, then a negative. I don't think a single line through this is a good idea. These down here are slope differences. So these tests in the last row here are our justification for whether we can draw one line through this and call it good. Is the difference between the beta 2 slope and the beta 1 slope significant? No. No, and no, but almost. So on the whole, it looks like happiness is not related to income. That's good news, right? As I know, graduate students don't necessarily have the best incomes, but I want you to all be happy anyway. So we made it. Yeah, so summary slide to wrap this thing up. The point of this unit is describing situations in which you need more than one slope to capture how one predictor conceptually relates to one outcome. So we started off with a 3-group variable, which needed 2 slopes. We looked at age, which needed 2 slopes, linear and quadratic. We looked at education, which we broke into 3 slopes, and then this happiness, which we broke into 4. But in each of these cases, it's one thing, right? It's education predicting this, or happiness predicting this. What if we wanted to look at all the stuff together? What if we wanted to know if education still related to income after you controlled for age, or vice versa? Can we do that?
Yes.
Yeah, we can. That's next week.
Yay.
Yeah, because most research questions are worded that way. Like, what is the effect of this after we control for all this other stuff that goes with it? So that's the big picture. More specific to that, dummy coding is what it's called. I'm trying not to use that term because I don't like it. Binary coding is maybe less offensive. I don't want to use the word dummy in statistics. People are already anxious enough about learning this stuff. That's not helpful language. No, seriously, like, statisticians are mean. Like, in our last unit, like the grand finale of the class, when we get to interaction terms, and interaction terms are quite complicated. There's a term that people use when you actually try to estimate a linear combination, and you know what they call it? A simple slope. Like, the hell it is? No. So yeah, here's a pro tip when you're writing your results sections. Never use the word obviously or clearly or evidently, because somebody's going to be offended that they didn't think it was obvious. So that's my thing here. But no dummy coding, binary coding. So the first method is more useful for nominal predictors. The one that we just looked at, the step function, sequential coding, is more useful for ordinal. We want to report direction, significance, and effect size for everything. Nonlinear effects of quantitative predictors, like linear and quadratic, for instance, or piecewise slopes, are another way that variables might take more than one slope. And we want to be able to test everything ourselves. Now, in terms of the code to do the ordinal happiness, the first model that I fit was just a linear slope of happiness, predicting income as sort of a point of comparison. Now, this one has one slope in the model. So do I need to look at like any of this? Not really. So the F for the model, if I take the t test statistic for that slope and square it, that is F. There is a 1-to-1 correspondence between the test of a slope and the test of a model if that model only has that one slope. It is the same thing. T squared is F. Likewise, the standardized slope for the single variable would be a Pearson correlation. That's R, and if I square it, I get this model R squared. It's the same thing. In this instance, it looks like there is a slight positive slope, but it's non-significant. So then here's the coding that it took to do the stepwise function. And unfortunately, I don't know of a way to do it faster in Stata, so it took relatively a lot of code. But the first is,
Copy paste.
yeah, copy paste, that's how. So this is covering all of the 0 cases, and this is covering all of the 1 cases. In R, I did the same pattern. So here's my model with the 4 sequential slopes. This is now our output from Supernova. So together, the slopes created an F of 1.2. They captured 0.0068% of the variance, so that's 0.6%, not even 1%, and a p-value of 0.29. So according to this model, happiness doesn't predict income. It accounted for no variance. I can still look at each individual slope, and here's something interesting, or potentially unexpected, I would say. This one's significant at the alpha of 0.05. So why do you think it might be that the model is not significant, even though it has a significant piece to it? That seems contradictory, right? Kinda. The answer is that F is an average. This is information captured divided by the number of slopes that it took. So I have 3 bum slopes and 1 useful one. On average, I have a bum slope. Another technical term. So your F can end up being non-significant for the model because it is a per slope evaluation. And if you have a bunch of non-significant slopes paired with a significant one, it's going to overweight it. So that can indeed happen. It can also be the case that your F is significant. You have a decent R-square, but none of your individual slopes are significant. That can happen too. We'll talk more about that next week. So our model is a bum model. The individual slopes we just talked about on the picture, but this is covering each successive difference on the ordinal scale of happiness. Here is the code to test the differences between them. I threw that in here as well, and those are all the differences. In Stata, here, actually these are the effect sizes, so this is the exact same code I said you could paste and copy there, and changing the name of the model, but otherwise this is the same R code as well to get these effect sizes. And then, of course, words. The end. 17 pages later, we finished example 3. All right. So these last 2 models, a piecewise model and an ordinal model like this, that's going to be your next homework. I'll let you know when that is available. It's not ready yet. Okay. Questions?
Yes, one.
One. Okay.
If you could go back up to a piecewise chart.
This one?
That one's perfect.
Okay.
Okay. So if you have your, make sure I'm looking at your intercept, so in this case the intercept at 1.
Mm-hmm.
If you subtract 1 off of all your x values, should the total across the row always equal that value?
Can you say that again?
So in other words, like for example, let's look at 5. 5
Okay.
minus 1 is 4. So if I add up across the bottom, should that always add up to 4, and the next one always add up to 3?
Yeah, that works.
I just thinking about like a way to make sure that you did your math correctly when you set up your table. Thank you.
Yes. Yeah, no problem. Other questions? All right, then would you like 20 minutes of your life back? Okay, you may have it.
Thank you.
Yay.
Thank you for
Very good.
being
Thank
here.
you.
Let me know if you need anything, okay? Have good weekends.
Good question. I'm
Bye, Zoomers.
still in strategy.
Well, okay, so